So just to remind you, we left off with discussing CPA security, right? So this is chosen plain text attack security. So I had mentioned what the security definition would be for in the case of CPA security. So we will consider the CPA indistinguishability experiment. Again, a key case generated by running the key generation algorithm, which takes the security parameter as input. The adversary is given the security parameter as input and oracle access to an encryption oracle, right. So essentially to this encryption oracle, the adversary can query messages of its choice and receive ciphertext that corresponds to those messages. Then A outputs a pair of messages M0 and M1 of the same length. Then a uniform bit B is chosen and the ciphertext, that is the encryption of MB, is computed and given to A. Again, the adversary continues to have access to the encryption oracle and outputs a bit B prime, and the output of the experiment is 1 if the adversary's guess for which among the two messages was encrypted, its guess B prime is equal to B, right. And then a private key encryption scheme phi consisting of gen, enc and dec algorithms is CPA secure if for all probabilistic polynomial time adversaries A, there is a negligible function such that the probability with which priv k CPA A comma pi of n is 1 is at most half plus negligible, right. So this is what we saw for the CPA security definition. Yes? So in EAV security, A was never querying M1 and M2, right. So in EAV security, A would only output a pair of messages M0 and M1 and receive C. A had no way to query plain text of its choice because there was no encryption oracle there. Okay. Exactly, yeah. So C, right, so it would be, so there it's not necessarily, I can see where your question is coming from. So you are thinking that sort of obtaining C implies A can query M0 or M1. But sort of the difference here is that A can exactly query M0, right, or whatever, Mi equals, M0, and then obtain exactly the encryption of M0. Whereas here, it submits a pair of messages and receives one of them. So it's part of sort of the challenge as opposed to an additional property that the adversary has. So in that sense, this part of the experiment is very similar. It is really, so in the EAV security, it's not that the adversary is asking for encryptions of plain text of its choice. It is really participating in order to get the challenge, in order to sort of observe this C. Okay, so there is a C that is observed across the channel and the adversary will know that this C corresponds to either M0 or M1. Apart from that, apart from the observation of the C, A knows nothing, right, whereas I will come to you in a second. Whereas here, A can query messages of its choice, receive ciphertext and then again observe C, which again corresponds to either encryption of M0 or M1. Is that distinction clear or is the confusion still existing? Okay, so I understand your confusion now. To the encryption oracle, the adversary is not submitting a pair of messages. To the encryption oracle, the adversary is submitting exactly one message and it will receive exactly the encryption of that message. Okay, whereas here, the adversary is sort of getting a challenge that corresponds to either of these two and it is trying to figure out which one of the two. Here, this is not performing any challenge. Does that make sense? So here the adversary, right, so you can think of this in the following manner, okay. So there is an encryption oracle to which the adversary can query M sort of like repeatedly, right, can perform this operation repeatedly and receive, so maybe let me call it something else so that I'll just call it M hat to differentiate the C hat from that C, where this is the encryption of K of M hat, okay. Then the adversary outputs M0, M1 and then receives C, where C is the encryption of MB. okay, and then A outputs its guess B prime, okay. I mean again A can still have access to the encryption oracle. So this bit is the same in both experiments, whereas in the CPA security experiment you have in addition this part which was not there before, right. So here, so you sort of see the difference between the two experiments now. So this additional oracle to whom A can query M hat and receive C hat did not exist prior. Only this part existed prior where A outputs two messages and it observes a ciphertext C that corresponds to one of the two messages. Okay? Yeah, your question?
Yes. Because A has access to the encryption oracle, what prevents A from then asking the encryption oracle, hey, here's M0, give me M1, give me, and then
yeah, very good question. Right, so exactly. So now his question was that A has access to encryption oracle, right, and we are still defining security in this sense. So what A could do is just query M0 to the encryption oracle and receive the encryption of M0. Similarly, query M1 to the encryption oracle and receive the encryption of M1. Okay, so there is nothing that prevents the adversary, right? So by our definition, we have not said that the adversary cannot query some messages. So what does this mean?
that there has to be something unique attached to each message for both the for A to not be able to basically fool the system.
So what do you mean by something unique?
Like either it has to be timestamp, or there has to be some other mechanism, or else A can simply just break the security by fooling the system.
So it is not that you need timestamp, right? So or maybe I'm not exactly understanding how your solution would work, but really what we require is that the encryption algorithm cannot be deterministic. In that every time you encrypt M0, the ciphertext should not be the same. So there is an additional randomness that is coming in, right? So every time you encrypt M0, maybe the encryption algorithm chooses a random string R and uses R somehow in its encryption to compute the ciphertext C. So the next time you submit the same M0, you may not get the same ciphertext, but decryption should still work. Okay, so that is really the idea. So you raise an important point actually, that for CPA security, the encryption algorithm cannot be deterministic. It should in fact be probabilistic. Okay, yeah. Sure, I will. Yeah. So right, so whereas in the eavesdropping security, for instance, even in perfect secrecy, the one-time pad is a deterministic encryption algorithm. So every time you encrypt the message M with a key K, the ciphertext is always M XOR K. It never changes. But for CPA security, we require that the encryption algorithm is randomized, and one such example is what we will see. Okay, does this make sense? Okay, so sort of this sets up for what I wanted to discuss next very well, which is exactly how do we build these CPA secure encryption schemes, and we will use a tool called pseudo-random function. So CPA security via pseudo-random functions. And so pseudo-random functions, or more specifically pseudo-random permutations, are practically instantiated using things like block ciphers. For instance, AES, the type of security that you expect to see from AES, although AES itself is not a pseudo-random permutation, the type of security that you expect to see from AES is something that is what we would formalize with a pseudo-random permutation. Okay, so what is a pseudo-random function, right? A pseudo-random function is a function that is seemingly random, okay? You know, like, so when you say something like a random string, you might have an idea as to what that could mean, because maybe you have thought of strings a lot more and strings being random a lot more than say a function itself being random, right? So essentially when you think of a function itself being random, you can imagine that a function, right, you can represent a function from n bits to n bits via some lookup table. Okay, so essentially when you have the all 0 n bit string, you look up sort of the string that's associated with it and output that as f of 0, and so on and so forth until sort of the all one string, right. So there are now 2 to the n entries in this table, and corresponding to each of this entry is some n bit entry that will determine what f of sort of this, say f of I here is. So this is 0, 1, etc. Up to what f of I is, right. So you can visualize a function in this lookup table, and then it can be well defined. So then essentially in a random function, the way to think about it is that every entry will be equal to a specific n bit value with essentially probability 2 to the minus n. So for every entry you will choose one possibility from these 2 to the n possibilities of the range with probability 2 to the minus 1. So you will choose 2 to the minus n. So you will choose it uniformly. Okay. So that is how you would think of a random function. Make sense? Right. So essentially f of 0 would be mapped to the all 0 string with probability 2 to the minus n and so on, and or so with some n bit string with probability 2 to the minus n. Okay. So then actually so I won't spend time on it because we have such a short duration, but you can in fact count the number of so maybe as an exercise I will ask you to count the number of functions f from n bits to n bits. Okay, so essentially choosing a function at random implies that you choose from these set of functions from n bits to n bits. Okay, so now this is just to give an idea as to what one means when one says a random function. But what is a pseudo random function, right? So for a pseudo random function, you consider a 2 input function. Okay, so you consider for simplicity, right, let the 2 inputs both be of length n, and it produces an n bit output. Okay, and you can think of this first input as your key, okay, and the second input as say some input that you're actually trying to like compute over. So I'll just call it input for now, and this is your n bit output. And essentially to sort of translate it to the setting that we are thinking of, this key that the pseudo random functions will also be called as PRFs, and I might use it interchangeably. I'll try not to, but I might. Essentially when we want to choose a pseudo random function, once we choose once we sort of key the function uniformly from some key that is chosen from 0, 1 to the n, it will fix the function that we are interested in. So that is exactly how a pseudo random function would operate. So I will not discuss anything more about this now due to shortage of time. So I'll just formalize it, and hopefully the formal definition of what it means for a function to be pseudo random is sufficient for us to discuss the CPA security. Okay, so I'll formalize the security definition of a PRF, and then we will see how such a PRF can help us build a CPA secure encryption scheme, right. So definition of a pseudo random function. Okay, so let f so we will call such functions keyed functions. So let me just call it be a keyed, that is 2 input function. We also assume that it is efficient to compute this f, that is given the two inputs say k and x, it is efficient to compute f of k comma x. This is for technical reasons. So if you refer sort of the definition in the textbook, what I am saying will become a bit more clearer with the discussion there. So such an f is a pseudo-random function if for all probabilistic polynomial time distinguishers D, there is a negligible function such that probability that D on input the security parameter with oracle access to Fk. So, you can imagine this to be sort of computing f of k comma x as y. Alternatively, we will also write this as Fk of x equals y. So, we subscript by k to indicate f of k comma x. Okay? So, this D that has oracle access to Fk will output 1 with almost the same probability as when it has oracle access to a function, a random function f, right. So, this f is chosen uniformly at random from all functions from n bits to n bits. So, sorry, the writing is a bit small here, but right, and this k is chosen uniformly from 0, 1 to the n. So, let me just take a minute to discuss this definition. Okay, so what we are going for is that so sort of this lookup table notion of describing a function from n bits to n bits will essentially show that there are a large number of functions, right, like exponentially large number of functions from n bits to n bits, whereas when you consider this two input function where you choose a function by choosing just an n bit key, this would be like a smaller number of functions to choose from. But an efficient distinguisher D that just has oracle access to some oracle, that it does not know whether it is a random function from n bits to n bits or this two input function f. So, if no efficient distinguisher D can distinguish between these two settings with greater than negligible probability, then we call this function f a PRF, okay, a pseudo random function. Okay, so this style of definition is not something that we have discussed so far. The fact that this has oracle access is similar to the oracle access that I discussed, even in encryption oracle context, but this is coming into play in a different way, right? So this is the definition of a PRF, and with which we will build a CPA secure encryption scheme. So it might be sort of a lot to take in at the start, so I'll leave it up there for a minute, and you can ask me if you have any questions.
Basically, the oracle just gives you a pseudo-random number.
So essentially, right, the oracle, so D has access to some oracle O. Okay, so D will query O on some x and receive y that is O of x. Okay, and then D is trying to figure out if this oracle O is a random function f from n bits to n bits, or this PRF with a key K where K is chosen uniformly. So, the description of F will be known to D. What is not known to D is the key of the PRF. Okay, essentially what we want is, the reason for this is the following, right. So, what we really want is to somehow be able to make use of a random function, right, when we try to build. So, particularly to your point, we want to build randomized encryption algorithms for CPA security. So, we need to sort of have some source of randomness, and the source of randomness that is coming in is via this PRF. Okay? Why can't we just use a random function? Because description of a random function is exponentially long, right. So, we can't pass that as sort of a key between the two parties who want to communicate. So, we instead use a pseudo-random function with this key k that is just of say length n, and then we are able to essentially get the functionality that we would get from a random function. Okay, so that is sort of the idea here. If just sort of the, just the fact that this is a 2-input function which can be keyed with a key k and which has a role such that it is not distinguishable from a random function by an efficient distinguisher, this understanding is sufficient for us to proceed. So, I hope that is something that we can all get on board with. Okay, so this f will be a PRF, right. So, this f is a 2-input function keyed with the key k, and since it is a PRF, it will be such that it's essentially the input-output behavior with an efficient distinguisher D will seem as though for every entry fk comma x, the entry y was chosen uniformly at random from the set of all 2 to the n bit strings. Okay, so that is sort of the idea to keep in mind. So, I will stop with that here, or maybe we can try an example. I won't want to take too much time though, right. So, let us try an example, right. So, I am defining f of k comma x, okay, as k XOR x. Okay, this is my definition of f. Okay, so is f a pseudo-random function? No? Why?
Because you can determine very simply, if I give the input as all zeros, then I'll get the key.
But D does not know key. Key k is kept secret from the distinguisher. So, in this context I did not mention it, but yeah, D does not know.
D can still send an input as key, right?
What do you mean?
D can still send an input.
So, D will not know that input is the key.
No, I'm saying D will send an input of all zeros.
Okay.
And if you're XORing it, then XOR with 0 is just that itself.
Yeah, but then you have to compare that with the key to say that this is indeed the key. D does not have that key. So, just take a minute, think about it, right. So, this is, what is the question, right. I am asking if this is a pseudo-random function. Our definition for a pseudo-random function is that there should not exist a distinguisher D such that it can distinguish between access to this and access to a truly random function. So, again, in sort of this very quick discussion of a truly random function, I discussed that for a truly random function, there are many input-output behavior that we would not expect, right. For instance, well, I can give some instances that might reveal the answer, but for instance, if you were to compute, you were to make 2 queries, say x1 and x2, and you receive answers y1 and y2, you would not expect there to be any relation say between this x1, x2 and y1, y2 if these were truly random, right? Because in a truly random function, this y would be chosen uniformly at random from the set of all n bit strings. So you will not expect any sort of relationship. Whereas, will that hold here? Yeah.
It won't hold. I can set basically complements of numbers. So I can set 1, 0 and then 0, 1 and send multiple complements. And if in response, because I'm XORing, if I get a predictable pattern.
So yeah, I want a more specific answer. So essentially what I want is the following, right? I want you to tell me what D will do, right? So D has some oracle axis. I want you to tell me what queries D could make, what responses, based on the responses it gets, how will D distinguish whether it's this scenario or this scenario. So a specific set of, maybe take a minute everybody, a specific set of things that D could do. For instance, D queries O on x1, receives y1, D queries O on x2 and receives y2. Based on this, can you come up with some pattern that maybe you will not expect to occur in a random function?
I can send the same input again and again if I keep getting the same answer, right?
No, you will always send the same input, and so this is deterministic, so you will get the same answer.
Okay, it's deterministic.
So this is deterministic. So this is just a function, right? So in a function, right, if you compute f of x or f of k comma x, it will always be the same thing. So this is not the encryption setting. So it's just a tool to build an encryption scheme. So let me ask you this: if O is f of k comma x as defined here, what will y1 XOR y2 be? So if this oracle O that D has access to is the f that is defined here, what will y1 XOR y2 be? So y1 is the answer that O returned on a query x1, y2 is the answer that O returned on a query x2.
It will be x1, x1, x2.
So you had an answer?
x1,
x1?
x1, x2.
Exactly, and this is because x1 XOR k XOR x2 XOR k is how y1 and y2 would be computed, right? So now this would be x1 XOR x2 in this case. Now if O were a truly random function, okay, so right, O is either this f of k comma x. So is this clear to everybody, this, why this is true? So if O were a truly random function, then essentially, right, this y2 would be something that is chosen uniformly at random from the set of all 2 to the n strings. Okay, so then this y2 to be such that it is, exactly y1 XOR x1 XOR x2, that it is exactly this fixed string will occur with probability 2 to the minus n, right? Whereas in this case, when O is this f, it occurs with probability 1. So this already is showing us that this f is not a pseudo-random function, okay? Is that making sense? Okay, so essentially, right, from a pseudo-random function, we sort of expect the properties that we would expect from a random function, right? That sort of the output of a pseudo-random function on some inputs would be as, they do not, the outputs do not exhibit any special relationships that we will not expect otherwise. Okay, so this shows us that this this particular f is not a PRF. There are, ways to build PRFs, but we will not talk from mathematical assumptions, but we will not talk about them today. So instead, we will go back to our original goal, which is to build a CPA secure encryption scheme, right? So now, consider a sender and a receiver, okay? So they both share a key K, and we want to build a scheme such that it's CPA secure, right? So, okay, now we have this, tool, a PRF, so assume pseudo-random functions exist. Now say the encryption algorithm is defined as the following. Okay, so to encrypt the message M under a key K, you just compute the PRF F on M and key K. Okay, and as we have just discussed, Fk of M would look as though it were a uniform string. Okay, so from this ciphertext C, the adversary will not be able to figure out what the underlying message M, because it is just some uniform string. Okay, so this is one reasoning, but will this lead us to CPA security? You're saying no, why? You're saying yes now. So the answer is right, it is no, yeah? So when you're saying it's deterministic, right, that is what you're trying to say, that every time you encrypt the message M, it will always be Fk of M. So this is a deterministic encryption algorithm. Even though we are using a pseudo-random function, the encryption algorithm itself is deterministic. So there is a way in which we need to introduce randomness to this encryption algorithm. Okay, so then what one could do, right, is the encryption algorithm, instead of just computing Fk of M, it can choose an R uniformly at random, okay, and then send Fk of R XOR M. Okay, in some sense you can even think of this as very similar to your one-time pad. In the one-time pad, you XORed the message M with a key K. K was a uniform string that was not known to the adversary. Now you are XORing the message M with, a random string Fk of R, which is not known to the adversary. Okay, so maybe this is how you can perform encryption. So, right, so when you want to encrypt a message M, the sender chooses an R at random and sends Fk of R XOR M. So, is there an issue with this? So, the issue of determinism, the encryption algorithm being deterministic is no longer there, because every time we want to perform an encryption, we are choosing an n-bit string anew, right? But is there any other issue with this?
The sender still has control of the random variable.
So
if it's a malicious sender, then it could just choose the same random variable again.
So I mean here, right, so in this setting, the sender is not malicious in the sense that, so the sender holds the key K, right, the adversary does not have knowledge of the key K. So in this setting, that is not what we are worried about, okay.
The adversary still cannot figure out what R is.
So the adversary, in the way this is written, R is not being conveyed, it's only Fk of R XOR M. But if R is not conveyed, can decryption succeed? No, right? So the receiver only knows K, the receiver knows F of course, but the receiver does not know R. So actually, if you now send the ciphertext R comma Fk of R XOR M, now can the receiver decrypt? Right, the receiver knows R, the receiver has K, so it can just compute Fk of R on its own, and then, so this is essentially the padding that we are now using to hide the message M and recover M. Okay, so this, as you can see, is a probabilistic encryption algorithm, because every time you want to encrypt a message M, you choose a new R, Okay, so then essentially the probability with which R would repeat, and because it's an n-bit string, that probability would be negligible, right. So essentially every time this message M would be padded with some fresh random looking string. Okay, so this will lead to actually something that is CPA secure. Yeah.
The algorithm, the F, what do you say, the PRF
Yeah.
is known to the adversary as well.
The PRF is known, but the key K to the PRF is not known. So essentially this key K is the key that is shared between the sender and the receiver. So the PRF is known, R is also known, but since the key K is not known, the adversary would not be able to compute what Fk of R is exactly. Unless somehow the adversary gets lucky and some other message in its sort of like query to the encryption oracle, some other message R prime, some other message M prime was padded or hidden with the same R.
And ma'am, even the oracle has access to the same K?
Yes, yeah, the oracle has access to the same K because you have to use the same PRF, that's right. So that's why I erased the definition, but yeah, the key K is generated and that is the same key that is used to key the encryption oracle as well. Okay, so let me just formally write down this encryption scheme, right. So CPA secure encryption scheme from any pseudo-random function, so from any PRF, right. So let F be a pseudo-random function and then we define the key generation algorithm as on input the security parameter, choose a uniform n-bit string K and output it. The encryption algorithm on input a key K that is an n-bit string and a message M that is an n-bit string. So we are considering fixed length messages and in particular messages of length n bits. Choose uniform R that's n bits long and output the ciphertext C as R comma Fk of R XOR M. Okay, and the decryption algorithm, right, on input a key K and a ciphertext C that consists of two paths R comma S, output the message M as Fk of R, that's the first part, XORed with S, the second part. Okay, so this is a CPA secure encryption scheme. So as you can see, it is probabilistic, right, because every time you choose a uniform R to encrypt the same message M, a new R is possibly getting chosen every single time and M is padded with that Fk of R. So any questions here? Okay, so how many of you like proofs? No, one yes, one no, two yeses. Proofs, kind of. So actually, yeah, I want to in fact go over the proof for why this scheme is CPA secure, and this will sort of introduce types of proofs to you that you may not have seen before, and like rigorous proofs of security are part of modern cryptography. So I did want to go over that, but I think I'm going much slower over all the things that I wanted to cover, that if I do the proof, I may not be able to go to say CCA security. But yeah, let's do it, right? So hopefully those of you who are not interested in proofs, after this proof get interested. So, so any questions on the scheme? Okay. So then, so maybe this is the only theorem we will see today. I mean, we saw other theorems, but I did not prove them, right? So let's try to prove the following. So maybe I'll just start there, so that I can have the whole board as I need it. Okay, so this is the theorem. If f is a pseudo-random function, then, so let's call this construction pi, okay. So I'm calling the specific construction pi. So then pi is a CPA secure private key encryption scheme for messages of length n. Okay, so this is the theorem that we will prove, right? So if f is a pseudo-random function, then this scheme pi is a CPA secure private key encryption scheme for messages of length n. Okay, so then what do we actually want to show here? We want to show that for all probabilistic polynomial time adversaries A, there exists a negligible function such that priv k CPA A comma pi, where pi is this encryption scheme. The probability with which A succeeds in this experiment is at most half plus negligible. Right? So if we show this, then we have shown that pi is a CPA secure encryption scheme, right? So that is a definition that we have agreed on. So is the goal okay? Is the goal clear to everybody? Okay. So in order to show this, typically, right, schemes that rely on a pseudo-random function sort of take the following approach, take the following template. You will essentially replace the pseudo-random function or the role of the pseudo-random function in the encryption scheme pi with that of a truly random function. Okay, and then you will argue that distinguishing between whether pi was instantiated with a pseudo-random function or whether pi was instantiated with a truly random function, distinguishing between the two can happen only with negligible probability by the definition of a PRF. Okay, and once you establish that as a second step, you will essentially view these steps as, instead of using a pseudo-random function, as a truly random function. And then when you use a truly random function in this place, in some sense you are essentially just doing the one-time pad. So the probabilistic analysis will show that the scheme that uses a truly random function in this sense, will be such that the adversary will be able to succeed in this experiment with at most like half plus negligible probability. So this is sort of the two steps that it will take. So towards the first step, right, consider the following encryption scheme pi tilde. Okay, so this is the encryption scheme pi that we have been talking about. I am introducing a new encryption scheme pi tilde. Okay, so pi tilde is exactly the same as pi, except that it uses a truly random function f little f in place of a PRF. Right, so essentially in the case of this pi tilde, you can think of, so there is no pseudo random function. So you can think of pi tilde as consisting of gen tilde, enc tilde and dec tilde. Gen tilde on input the security parameter, instead of choosing a key for the PRF, will choose f uniformly from set of all functions from n bits to n bits. Okay, and then on input a key k and a message not a key k, so there is no longer a key k in this setting. So on input, I guess the key f and a message m, choose uniform r and output the ciphertext r comma little f of r XOR m. And then on input, again this f and a ciphertext c, that's r comma s, output the message m as little f of r XOR s. Okay, so essentially what pi tilde does is wherever the pseudo random function f was being used, we now use a truly random function little f instead. Okay, so that is exactly what pi tilde does. Okay, so let me erase this and just write that down in words. Okay, so pi tilde consisting of gen tilde, enc tilde and dec tilde does the following. So gen tilde chooses a uniform f from n bits to n bits and outputs it. And enc tilde and dec tilde use f instead of fk. Okay, so this is pi tilde. Okay, so one point to note here, pi tilde is not a well defined encryption scheme. Okay, the reason for that, it's not following the syntax of a well defined encryption scheme. The reason for that is the key that is output by the key generation algorithm gen tilde is the description of this function little f, and that is exponentially long. And we have discussed that all of these algorithms that we will consider will be polynomial in the security parameter, right? So whereas this is not something that is polynomial in security parameter, we are using this pi tilde only for the purposes of the proof, and for that it is well defined and that is sufficient for our purposes. So it's not actually an encryption scheme that we can use, but it's well defined for the purposes of the proof. Okay, because even though the key length is exponential, it is fine for us to use it for our argument. Okay, so this is pi tilde. And now we will show the following, right? So as a first step towards showing this, we will show that probability priv k CPA a comma pi of n equals 1, right, which is the goal that we had here, minus probability priv k CPA a comma pi tilde of n equals 1. So the difference between these two probabilities, essentially the difference with which an adversary A succeeds against the experiment with pi, and in the experiment with pi tilde, the difference between those two probabilities is at most some negligible function. Okay, so this is what we will show. So is this statement okay? So is this inequality making sense? As in how we obtain it is a different question, but just the mathematically it is making sense? Bigger, yeah. Okay. So why can this inequality be true? So I'm saying this is what we want to show. Can you think of why this inequality can be true? Yeah.
If an adversary cannot non-negligibly make out the difference between the output of a random encryption scheme and a pseudo-random encryption scheme, then they cannot deterministically, basically find an attack vector for. Like, if you can't differentiate whether it's random or not, then you won't be able to make a sure decision or a sure conclusion about whether what you're finding is correct.
So I'm not following exactly. So maybe try to be a bit more specific in your answer. Think about how you would make it a bit more specific. But what is the difference between pi and pi tilde essentially? Yeah. And
So if the difference is not negligible, we would be able to decrypt the data back.
so that is not necessarily true. The decryption working may not depend on this necessarily, but yeah, so your point actually is more to the point of why we are discussing between these two, which is that the difference between pi and pi tilde is essentially the difference between using a truly random function and a pseudo random function. And if say this were not true, in some sense what we are saying is that there exists a distinguisher. I mean, although it's not an immediate step, but that's what we will show. There exists a distinguisher that can distinguish between a PRF and a truly random function. And because f is a PRF, such a distinguisher cannot be able to, cannot distinguish between a PRF and a truly random function with non-negligible probability. So if this is true, it would imply that f is not a PRF, right? So, and that is exactly what I will argue now, okay? So it's not exactly a proof by contradiction. So sort of this template of a proof is called something called proof by reduction, and you may not have come across it elsewhere. Maybe in your theory of computation course you might have seen something to this effect, but otherwise you may not have really seen this method before. So that's another reason why I wanted to spend some time on it. Okay, so now in order to show this, let's consider this distinguisher D. Okay, so let us consider the following distinguisher D. Okay, so this distinguisher D is taking part in sort of the PRF definition, right? In the PRF definition, if you recall, D had access to either Fk or D had access to right. So F was a PRF if the probability with which D outputs 1 here minus the probability with which D outputs 1 when little f is a truly random function is at most negligible, right. So essentially D has an oracle that takes in n bit inputs and produces n bit outputs, and D is trying to distinguish whether this oracle is Fk or F. Okay, so we will now consider the following distinguisher D, okay, so which has oracle access to O from n bits to n bits, okay. And what this D will do will essentially try to simulate the PrivK CPA experiment to this adversary A, okay. So in the PrivK CPA experiment, what does the adversary expect? The adversary is given, input the security parameter, right. So so fix this adversary A. So I did not write this down anywhere, but fix the adversary A. So run A on input the security parameter, okay. And now because we are in the CPA experiment, this A might ask query to its encryption oracle, right. So when A queries the encryption oracle on a message M, right, this D will do the following. Okay, so I mean D is trying to simulate priv k CPA to A. So A is not actually participating in it, but D is trying to simulate it. So D is not actually honestly generating any key K by running the key generation algorithm. So instead what D will do, it has access to this oracle O. So D chooses uniform R in 0, 1 to the n, okay, queries O of R to obtain say some W, okay, and then returns R comma W XOR M to A. Okay, so when A queries the encryption oracle, so notice A is being run by D, right? So A is not actually in the priv k CPA experiment, but in the priv k CPA experiment, A has access to an encryption oracle, and D is trying to simulate that access to the encryption oracle, and D does it in the following manner. So when A makes an encryption oracle query to on a message M, D itself chooses a uniform R. D has some oracle O. This O is either Fk or little f. And D queries O on R to obtain W and returns R comma W XOR M to A. Okay, then when in the priv k CPA experiment, at some point A outputs messages M0 and M1 of the same length, right? So when A outputs these two messages, D does the following, choose uniform B in 0, 1, okay. So again D is doing it on its own, not by taking part in any priv k CPA experiment. Then again choose R from 0, 1 to the n, or maybe I will call it R star because it corresponds to the challenge ciphertext. Query O of R star to obtain W star, and then return challenge ciphertext as R star comma W star XOR MB. Okay, so when A outputs messages M0 and M1, D chooses the uniform bit B on its own, and then essentially returns the ciphertext R star for a uniformly chosen R star, comma O of R star XOR MB for that B that it chose. And when A continues to make encryption oracle queries, it answers as it is here, right? Then finally when A outputs 1, D will also output 1, right? So if A outputs, A will output B prime, right? So when A outputs a bit B prime, which is its guess for B, if B prime equals B, output 1, otherwise output 0. Okay, this is what this distinguisher D is doing. So I'll just leave it up here for a minute, take a look at it and ask me. So exactly why we are doing this I'll come to in a bit, but just make sure that the steps are making sense. So what happens when D's oracle O is Fk, the pseudorandom function Fk? What is A's view in that case?
It should be the same as, if it's CPA secure, then it should be
No, so it is, we are not assuming CPA security, right? So we are trying to prove it is. So the only assumption is F is a PRF. So the question is, this is how we have defined the distinguisher D, okay? So now D has access to this oracle O, if this oracle was fk for a pseudorandom function f, then what is the view of A? Like what would it seem like to A? What would be D's behavior seem like to A?
Can you please repeat what E does?
This, okay. So essentially, right, so we are defining the following D which has oracle access to O. Okay. So for this fixed A, D will run A on the input, the security parameter. When A asks an encryption oracle query, so when A queries the oracle on a message M, D will choose a uniform R, query O of R using the oracle it has access to obtain some W, and return R comma O of R XOR M to A. Okay, when A outputs messages M0 and M1, D chooses uniform bit B to figure out which among these two messages it will choose, and then for that message chooses an R star, that's a uniform n bit string, query O on R star, and then return the ciphertext or the challenge ciphertext as R star comma W star XOR MB. And finally, when A outputs a bit B prime, if B prime equals B, D outputs 1, otherwise D outputs 0. So now the question is, if this O was Fk, which experiment would it seem like to A that it is taking part in? So if D's oracle O was Fk, right? So then what happens is here when A makes an encryption oracle query, D will be querying Fk of R and D will be returning Fk of R XOR M. Similarly here, D will be querying Fk of R star and D will be returning R star comma Fk of R star XOR MB. So what does this seem like, the first three steps? Sorry? No, F is pseudorandom, but to A, which experiment is it taking part in?
A cannot, there is no difference
Between?
between the two experiments.
Which two experiments?
The one using the pseudorandom generator and the one using the random number oracle.
So, I mean, we are not yet there, that's not yet, we are not yet at a place where we can establish that, right? That is what we are going to establish. But essentially, right, to A, it would seem as though it is taking part in the PrivK CPA A comma pi experiment, right? Because in the PrivK CPA A comma pi experiment, A, will be run on some, A will receive some security parameter, then A will expect encryption oracle access, where the encryption would be carried out exactly as it's carried out here. Because in pi, when A has an encryption oracle access here, right, the encryptions would be returned such that encryption of M would be C, where C is R of Fk of R XOR M for a uniformly chosen R. And that is exactly what's happening here. When A makes an encryption oracle query, you choose a uniform R. When O is Fk, you query you query O on R, obtain Fk of R and return this. So this is exactly how the encryption oracle would behave in the case where it is PrivK CPA comma pi. Okay, and you can sort of see the rest of the things would also follow. Whereas when the oracle O is a truly random function f. Okay, so the oracle O is a truly random function f. Then how would this experiment seem like to A? Somebody say something. So this form of encrypting, what does it seem like? Which encryption scheme will follow this form of encrypting? Pi tilde, right? Exactly. So when the oracle O is a truly random function, this is exactly how the encryption oracle would behave in the case of priv k CPA A comma pi tilde. Okay, so essentially, right, I don't want to take too much of your time, but depending on whether the oracle is Fk or F, one can argue that either A is in the priv k CPA A comma pi experiment or in the priv k CPA A comma pi tilde experiment. Okay, depending on whether the oracle O was Fk or F. Okay, and now since whenever the adversary succeeds in this experiment, the distinguisher D, so we have defined the distinguisher D to output 1 when the adversary succeeds in this experiment, right. So when A outputs a bit B prime such that B prime equals B, D also outputs 1. And by the definition of a PRF, the difference between D outputting 1 in this scenario and in this scenario is at most negligible. So the difference between the adversary A succeeding in the priv k CPA A comma pi experiment and in the priv k CPA A comma pi tilde experiment should also be at most negligible. Okay, so this is sort of the idea behind how we would show this inequality, and such a proof is called a proof by reduction, because essentially you are well, this is a very fascinating way to prove things. We are essentially running the adversary A as a subroutine inside a distinguisher D that is trying to distinguish between the assumption that you have already made, and D would simulate the correct environment to the adversary A, and if it manages to simulate that correct environment and A is still able to break the security, that would imply that D could break the security, right. So this is sort of the high level idea. So any quick questions here, or is everybody completely lost? Yeah.
So basically, can we consider it as two separate experiments running
Yeah.
the same messages?
Yeah.
And one experiment is using a truly random number generator, the other one is using a pseudo random generator, and basically both in the same, for the same message, both should basically either succeed together or fail together. And if the difference between both succeeding together,
So it is not about succeeding together or failing together. So really, depending on what O is, we are either in one world or the other, right. So depending on what O is, we are either in the priv k CPA A comma pi experiment or in the priv k CPA A comma pi tilde experiment, right. And then because D cannot distinguish between O with non-negligible probability, A should also be not able to distinguish between whether it's in the pi experiment or the pi tilde experiment with non-negligible probability. Okay, so actually, since we are running much over time, then I thought of, so there is a second part to the proof that maybe I'll just discuss very quickly. So essentially, the reason to establish this is now that finally our goal, like I said, is to prove this, right, is to prove this inequality. And now, because we have the difference between these two inequalities is at most negligible, it is sufficient for us to focus on the probabilistic analysis of this term. So essentially, bounding this term with a truly random function is something that we will argue probabilistically, right. And like I mentioned, as long as this R does not repeat, right, this message M is essentially, it's as though the one time pad is being performed here, because it's padded with a truly random string. Okay, so to bound this probability, you will essentially, because A is restricted to making polynomially many queries, because it's a probabilistic polynomial time adversary, we can bound the probability with which R can repeat. Okay, so if A makes at most q queries, right, for R to repeat, it should happen with probability at most q over 2 to the n, okay, and you can sort of see it pretty easily. So I'll ask you to take a look at it later, right? So, and as long as r does not repeat, this is essentially the one time pad, in which case by sort of what we have argued before, the adversary will not be able to figure out if M0 or M1 was the encryption of this R star, R S star, whatever it is. So that is how we would complete the proof. So if there is interest after T, I'll complete the proof, otherwise I'll let you guys go. So we can break now. Any quick questions? Okay, yeah, we can break now then.